Affordability Analysis, an examination of the efficacy and cost-effectiveness of solar panel windows utilizing reflector total station. By Jenna Chapman, Joshua Clanton, Daniel Durheim, Emily Gill, Dabrion Gonzalez, Kendall Hale, Christian Montgomery.
So, for this project we are using RTK to determine the precise location of our solar panel. We then are going to determine how much money could be saved a year at the project location once our solar panel is installed. While utilizing the sunlight measurement applications, we determined how much energy can be produced over the year, and then subtract that number from the total energy bill to produce our final yearly savings number. Alrighty, so the equipment used to perform this project is a real-time kinetic positioning system that pinpointed our latitude and longitude, a total station which we used to record precise measurements of the window corners, and with that we used a Leica reflector prism so we could measure these points from long distances away. And finally, we used the sun calculator application online that gave us the number of sunlight hours available for this location over a specified time.
Why solar energy? Transitioning to solar-powered energy sources has many benefits. It is a renewable energy source. The solar panels produce electricity by transforming the energy of the sun. It is a clean source of energy. No harmful greenhouse gases are emitted into the atmosphere. Low operating cost. The photovoltaic process that transforms sunlight into electricity does not require any fuel and has no viable cost after installation. The typical American family spends about $2,000 annually on their electricity bill. If families switched over to solar energy in about 20 years, on average, they would save approximately $17,000. In College Station, Texas, the highest estimated amount of money that could be saved by switching to solar panels on a home was $35,000 in 20 years.
Methods fieldwork. We started with RTK to take an accurate control point at our survey site. So we chose a location where both of the windows were visible, so we would be taking only one control point with RTK instead of two. So once we had our control point, we placed our total station over it, and then we shot a back sight and imputed those two coordinates into our total station before surveying the window points. So once we actually started taking the window points, the corners of the windows, we made sure to approach each window in the same order for consistency. So we did the upper right corner first, then the bottom right, the bottom left, and lastly the upper left. So our prism rod was held as close to the corner as possible while still being able to be caught by the total station. So the first window we did was on the southwest side of the house, and the second one was on the southeast side. And we chose to compare these windows as they were on different sides of the house with different surroundings. So our analysis of which window would be suitable for solar panels was more conclusive. While on site, we also made sure to take note of the surroundings of the windows. So, for example, window 1 is prefaced by a large awning that provides shade and is surrounded by bricks that hold in heat, while window 2 is flush with the wooden siding and isn't prefaced by a large awning, meaning it's getting less shade. And so all of these affect the amount of sunlight and heat that the windows are receiving.
In order to successfully analyze the total station points we took and utilize these for cost analysis, the project team had to input the latitude and longitude of each window into the sunlight calculator database in order to obtain the daylight duration each window would receive in the fall and in the summer. Window 1, facing southwest in the driveway, receives 10 hours, 32 minutes, and 19 seconds of sunlight in the fall. Window 2, that is located in the back of the house, facing southeast, receives 10 hours, 32 minutes, and 17 seconds of sunlight. In the summer, window 1 gets 13 hours, 52 minutes, and 59 seconds of sunlight, and window 2 gets 13 hours, 52 minutes, and 57 seconds of sunlight. The total usable amount of sunlight hours calculated by the Google Sunroof project is 1,657 usable amounts of hours per year. This data is important because the RTK provided us with the exact location needed to calculate the amount of sunlight the points get each day in the fall and summer. This helps with our overall goal because we saw the difference in the daylight duration, which wasn't much, so our deciding factor in which window to use for the solar panel tech is attributed to the environmental factors that will be discussed in the upcoming slides.
Results, GNSS applications. RTK, total station, and a reflector prism were used to accurately measure the exact points of the window corners. And so by doing so, the difference between each window in the sun calculator could be analyzed to determine whether or not either window would, have more or less sunlight. And so by using RTK, total station, and the prism, we could take the four corners of the windows and average those to have two sets of coordinates that could be inserted into the sun calculator. So instead of using just the address or one set of coordinates for the entire house, we could do the two windows to see if there would be a difference between the two. But there was only a very small difference of sunlight received, or number of hours of sunlight, between the two sets of coordinates that were averaged for the windows. So the house would benefit from solar panels nonetheless. There's not that much of a difference between which window, but the difference in which window would gather the most sun chalked up to environmental differences in the surroundings of the windows is concluded in the rest of our results.
Results, sunlight analysis, environmental factors. There are a few key environmental factors to take into consideration regarding the placement of the windows. The sun rises in the east and it sets in the west. Therefore, any eastern and western facing windows will receive more sunlight as a result of being directly in the sun's path. Tree cover also plays a large role in how much sun comes through a window. If one is looking to collect the most sunlight as possible to harness energy, the area should be free of any trees and/or other objects that would block the sun from reaching the windows. Therefore, window 1 on the studied home is the most optimal window to harness sunlight because it is facing southwest, meaning that it will receive the most sunlight due to its placement on the house, and it is far from trees, awnings, and other obstacles that could potentially block sunlight.
Next, for our on-field survey work, we used a Leica total station and backside RTK in order to determine the most accurate processing points visualized in the image above. We found latitude, longitude, and elevation, and we based them around window 1 and window 2. Window 1 is where we will actually be analyzing our solar panel installation, while number 2 was just another sample. This data was processed through ArcGIS Pro, and it gives us a better representation and usable data files in order to determine the exact energy sustainability process, and in connection with the sun calculator and the amount of sunlight hitting the house at the southwest corner and the southeast corner of those two windows. The backside provided our true north point for our total station in order to get the most accurate position method available for each corner of the window. This portion of field work is more so necessary to determine the correct elevation of each sides of the house. From there, we can factor in sun incidence in accordance with our future installation plans of solar panel technology.
Hello, my name is Daniel Durheim, and I will be going over the cost-effectiveness analysis of the data results of our energy sustainability project. So we found that the average household energy usage in the state of Texas is 1,174 kilowatt hours per month, which translates to 14,088 kilowatt hours per year. On the house that we studied in College Station, which we studied two windows, window number 1 we found receives 14.1 kilowatt hours of sunlight per month based on the location and the size of the window. And of course, this varies depending on the time of year. in the month of June in College Station, a window 1 meter squared will receive 4 to 5 kilowatt hours of energy, and in December that will go down to anywhere between 3 to 4. Based on the average price of solar panels, which is listed in the slides, we can deduct that the cost of a household in Texas, which is the average household energy usage, would be paying $36.35 to $47.62 per year. And by comparison, the average household energy bill in the state of Texas is $1,614.24 a year on energy bills. So by installing a solar panel, we can find that the homeowner can save between $1,566 and $1,578 on energy bills per year. Of course, this does not take into account the price of installing a solar panel, which is usually between $7,000 and $12,000, but these costs would be offset within about 5 to 10 years. Additionally, we found that a solar panel system generating an average amount of energy usage for a house will save an average of 7.6 metric tons of CO2 emissions per year, also the equivalent of planting 72 trees per year, and the equivalent of driving a whole 18,555 miles less per year.
In conclusion, this study shows that solar panel windows, when they eventually do exist and are operational, are a cost-effective and sustainable alternative to conventional electricity for the average homeowner. A homeowner can save around $1,500 per year on their electric bill while saving the planet. By using RTK GPS, the team was able to obtain the exact coordinates of each window, and using those coordinates, then analyze the importance of window placement. In the future, homeowners may be able to use GPS locations on their phone to determine the best solar panel window placement instead of using high-tech GPS technology. This project found the ideal window placement to be facing the sun's path so as to not limit sunlight hours. Also, anything obstructing the window should be removed for the same reason. In the future, more homes can be studied using this method as solar panel technology progresses.